Hello all. Today we will be discussing about a very interesting topic, and this is going to be based on computational fluid dynamics. So most of us would have seen uh, the ship floating on the ocean, catamarans floating on the ocean. We have seen the sails, sailing across the sea. On different occasions, we would have watched it, and often people would have wondered, like, how this particular gigantic structure simply floats on the ocean. So, of course, there are machines and related machineries like engine systems, everything. Uh, as we have in other transportation vehicles. So, like trains or trucks or buses, there are mechanical devices, mechanical systems in ship also, and those are systems that can drive the ship. So how it drives the vehicle on the roads, and how it uh, drives or rolls the train on the track. So for anything that needs to move, there is some energy required, and that energy is supported or provided by the prime mover. So prime mover is nothing but anything that has got a rotary device, a rotating device, a power generating device is what we call as prime mover. So this prime mover moves that vehicle, and hence the vehicle rolls. So similarly, these floating structures make use of the principles of buoyancy, and based on buoyancy, uh, the ship floats, the sail moves. And apart from buoyancy, buoyancy is something. It's a principle. It's a mechanism with which a system remains stable on water. Okay, water, or it can be any liquid. Okay, so here, since it's ocean or sea, okay, we generalize it as water. So apart from the engine and apart from the principles of buoyancy, there is also wind, which is a very important parameter here. A wind will, move the system, and there will be, from the positive point of view, we can say that there is a push, and similarly, there can be a drag also, like how we, uh, you know, discuss in terms of aeroplanes or aircrafts. So there is a lift and a drag, and this lift and drag compensation uh, lifts the aircraft or makes the aircraft fly. So similarly, this push and pull, the pitch and roll, okay, that is what we call for a ship or a sail, etc. For anything that is floating on the water. Okay, so here we see a particular submarine, and this particular submarine is moving uh, in the ocean, and a part of it is submerged under the water. A part of it is above the water, and this is moving at certain knots, say about 16 knots, close to 16 knots, and we are supposed to be finding out or determining the parameters, okay, which is related to hydrodynamics. So we are assuming that there is a ocean. Okay. Instead of calling it as an infinitesimal ocean, because from one frame of reference, okay, from a single observer's point of reference, the ocean is supposed to be an infinitesimal subject. So here we are going to take a finite uh, boundary for the ocean. So we are going to define that this is going to be the specific boundary, and within this particular boundary is that particular ocean which is accommodated. And in this particular ocean, there is a submarine that's floating. Okay, so this is floating or moving at a speed of 16 knots, and we are going to calculate the hydrodynamic forces. We are going to find out the velocities. We are going to find out the circumferential velocities. We are going to find out the shear stress parameters. We are going to find the frictional parameters between the submarine and the ocean. Okay, so we are going to find out very complex parameters here. So what we are going to do is we are going to define what is going to be the fraction of volume, fraction of air and fraction of water, because that is very important. A part of the submarine is above the water, a part of the submarine is below the water in this particular case. So we need to define like what percentage of the submarine is going to be exposed to the air and what percentage of the submarine is going to be below the ocean. Okay, so here there are two different parameters, two different subjects. One is going to be air and the other one is going to be water. Okay, so it's a combination of two different structures. So there is going to be a fluid and a structure contact. So this is a typical fluid structure interaction problem. The structure is submarine, the fluid is ocean. Okay, and then the third entity is air. Okay, so we are going to define one single parameter that is called the velocity. So the speed with which the submarine is moving, which is almost defined as 16 knots. And then we are going to find out like what would be the time. So we are going to design this particular system, say for 10 seconds. So 10 seconds is going to be the time for which this particular submarine is going to float. Okay, so now, okay, what we are trying to do, you need to visualize it this way. Okay, the particular submarine must be traveling from one country to the other country, and the distance will be say about 6,000 kilometers or something. And we are not going to consider the entire 6,000 kilometers. Instead, we are going to define a specific boundary, a specific region, and to that particular specific region, we are going to find out, okay, when this particular submarine is going to travel at 16 knots speed, okay, what will be the distance traversed. Okay, so we are going to find out parameters like turbulent energy. We are going to find out the turbulent viscosity. We are going to find out the total turbulent length, and we are going to find out what will be the static pressure. We are going to find out the dynamic pressures, and we are going to find out the other hydrodynamic parameters, like the circumferential stresses, okay, across the the boundary of submarine, and we are also going to find out the normal forces and the radial and axial forces that is going to act on the submarines. And apart from that, we also have designed a specific system, okay, which is going to be like a bluff body. A bluff body is nothing but a body that is going to hinder the path of the waves. So there is going to be a certain waves which is generated, okay, when the submarine moves in streamline motion. Okay, so we are going to assume that the submarine is moving in streamline motion, and when it moves and when it penetrates, cuts and penetrates the ocean, there is going to be huge waves which is going to be generated, and these waves are going to uh, strike certain bodies, okay, which we call as bluff bodies, and we are going to study like how these bluff bodies are going to change the hydrodynamic behavior of the submarine. Okay, so that is an objective. Okay, and the other objective is to find out like what other design parameters. So this involves a lot of design. So it is not so simple. This is also exactly like how we design the aircraft. The first thing is about designing the hull of the submarine. Okay, and then we need to design the other systems. So there will be a power generation system. So there will be a propeller, and the propeller will be connected to the propeller shaft, and the shaft will be connected to the engine. Okay, and this engine is going to be powered. Okay, so it can be nuclear powered or it can be powered through fuel. Okay, so there are different processes how the powering is done. Okay, so let us assume that there is a certain power, and because of that power, there is going to be a certain velocity, and that velocity is about 60 knots. Okay, so that's the input parameter what we have. Now, uh, let's see, like this is going to be the shape of the submarine. Okay, so the submarine is going to be connected because I want some 3 or 4 different bluff bodies. So as I told you, bluff bodies are nothing but the bluff bodies are the bodies that are going to hinder the path, the wavelets which is formed from the submarine. Okay, so here this is a mathematical modeling, and we cannot model it using finite elements as we model the other structures. So previously we have seen the case of an impeller, the industrial, the induced draft fan radial impellers, where the impeller design was done using a 3D solid model CAD system, and then it was meshed using one of the FEA tools, the CAU tools, and then that was meshed using hexahedron elements as well as hybrid elements. And then we applied the loads and boundary conditions, and then we performed a structural simulation. And likewise, we also performed a normal mode simulation, and then we checked for the operating frequency, and then we also found out the random vibrations and stuff like that. Okay, so now that particular system is called the finite element analysis, finite element method. Okay, so breaking the geometry into well-defined geometries like triangles and quadrilaterals. Okay, or its second order or third order derivatives. Okay, so here the method that we are going to adopt is called finite volume method. So these structures are going to be broken into individual cells. We call it the cells, and these cells can be considered in 2 ways. One will be the solid cell, and the other one is going to be fluid cells. Because this particular domain that we are going to focus here is completely on computational fluid dynamics, and CFD is related with fluids and fluid systems, and this will be completely focusing on Navy stroke systems formulations, and then the other formulations based on the problem, the kind of problem that we are using. So here, this particular problem, we know that the hydrodynamic parameters are going to be a very complex system. Okay, so it is not going to be your like quadratic systems, or it is not going to be your second order or a third order kind of system. It's going to be a partial differential systems, and this is going to have a lot of unknowns, parameters are more. You will have say about x number of variables and x number of unknowns also. Okay, so the system is going to be complex. So now in order to solve it, we cannot be using finite element method because that's going to be a very, very complex task. So we have different other formulations. So one is boundary element, a finite volume method, and then we also have boundary element method. Okay, so these are basically used for fluid domains. Say it can be fluid dynamics and anything related to fluid dynamics, like acoustics, noise, etc. All kinds of acoustic systems are all modeled, from the CFD, the computational fluid dynamics. So here we have a submarine, and the submarine is going to be connected with 4 bluff bodies. So these bluff bodies are going to be exactly back. And now I don't want to create 2 or 4 different bodies, so I just connected it because this is not going to have a big impact. Okay, there will be of course some kind of changes in the flow. Okay, but then that's going to be very negligible. Okay, but still there will be a change. Okay, so now what we do is we are going to define a computational domain. Okay, so now this is going to be my computational domain, which means this is going to be the size of my ocean. Okay, so this is the complete universe, I mean the planet for this particular problem, and we can see that any region which is below the submarine is supposed to be the ocean, water, and anything above that is going to be considered as air. Okay, and in between we have the submarine, the solid body, and it's made aerodynamic. So we have made it aerodynamic, yes, and then there are other systems also connected to that. Okay. So now once I define what is going to be my system and what is the problem definition. Okay, and once the problem definition is defined, then we need to key in certain parameters. We need to make the software, the system understand what is the kind of loading pattern that it's going to experience. So now since we have given an input detail as 60 knots as the velocity with which the submarine moves. Okay, now this is going to be considered as an external aerodynamic system. Okay, so this is not an internal aerodynamic, this is an external aerodynamics. So anything within this particular submarine is to be omitted. So we don't have to worry about what is internally, what is there inside of the submarine. We are just worried about the aerodynamics, the outer system, the outer part. So now the geometry is going to play a major role in this system. Okay, the external geometry. So the shape is going to be a very important task. Okay, so now the external aerodynamics is going to be performed, the external flow simulation. Okay, and we are going to define this as a transient system because as I mentioned, the submarine is moving from one point, this point to this point, and it is going to be 10 seconds. So in 10 seconds, the submarine is moving from coordinate 0, 0, 0 to along the x-axis. So along the x-axis, it's going to travel say about 100 meters or say 200 meters. So 10 seconds. In 10 seconds, it's going to travel say let us say 100 meters. You can see. Okay. So now this binding box, okay, could be defined as a 100 mm box, and 100 meter box, and in this 100 meter there is going to be not 100 meters, let us say 1 kilometer, and this submarine length is going to be about say 25 meters. Okay, so a 25-meter submarine is going to travel on a virtual cube, okay, whose length is about 1 kilometer. Okay, that way we can say, and at the rate of 60 knots. That's how the problem definition can be given. Okay, and then we define, like, this is going to be a surface phenomena. Flow is going to be a surface phenomena, and then we are going to define, okay, what is going to be above the surface and what is going to be below the surface. So we are going to say that there are two invincible fluids, okay, two invincible fluids which is going to interact on one single boundary. So whatever red color region that you are going to see, you are seeing here, let's say that is the boundary, and above that boundary is air, and below that boundary is water. Okay, so how the system is going to work. Okay, so here I am performing a simulation, a transient simulation, a time dependent simulation for 10 seconds, and each 1 second is going to be divided into 0.01 seconds. Okay, total is about 10 seconds, and each 1 second is going to be divided into 0.01 seconds. Okay, and that is how I am defining this boundary. Okay, so once I am defining this boundary and I am defining the system that this particular submarine, the object there is going to travel at a speed of 60 knots. Okay, so the next is going to be the mathematical simulation, the calculations, okay, based on which there are certain goals that I am going to define. Why I am defining a goal is I need to understand, like, there are certain outputs which I need, and the outputs that I want are like, static pressure, dynamic pressure, then we need a volume flow rate, then we need average velocity, we need the circumferential velocity, we need the turbulent energy, and we need the normal forces. What are the forces which is acting on the structure, okay, the submarine walls. And we also need to understand, like, what are the shear stresses, because there is a surface, the red color boundary what you see is a surface which is connecting the air and the water. Okay, so that's a continuum surface. Okay, and that is going to act as a layer, a shear layer. So there is going to be shear between air and that surface, and shear between water and that surface. Okay, so this surface is going to indirectly create a shear force between air and water. Okay, that's what I am trying to define. Okay, and then I am trying to find out what is the mass fraction of air and what is the mass fraction of water. And I also want to find out what is the volume fraction of air and volume fraction of water. So these are all the most important parameters, the hydrodynamic parameters, which I need to figure out. Okay, so now I am performing a simulation, and I define the transient system, and now I am going to find out, like, how my flow is going to become. So the simulation, I have worked out earlier, and once I have defined the simulation parameters, say I have the general settings here, I define it's a time dependent system, then there is a free surface. So this red color surface what I showed you is a free surface, and now this is an external aerodynamics. Okay, and then I have the other conditions. The velocity across the x direction is going to be 60 knots, and then I also have the concentrations, the initial fluid, and what is the initial fluid? The initial fluid that the submarine is going to be in contact with is water, and then there is going to be air on the top. So I am defining that particular system, that is at minus 0.0004 meters there is water, at 0 meter it is water, and 0.006 meter it is air. Okay, so this is the geometrical definition of what you see there in the geometry. Okay, now once I have defined that, okay, I am going to run the simulation, and after so many iterations, I have defined the goal, the objective. What are all the objectives we need to find out, and then I'm going to create a global mesh. So this is going to be the fluid dynamic mesh, the computation fluid dynamic mesh, or we can call it as grids. Okay, so now how small the grids are. If the grids are going to be refined, okay, we call it as narrow channel enhancement or refinement. Okay, and the maximum the refinement ratio is at that beautiful the results are going to be, that accurate the results are going to be. Okay, now I am going to use my computational system. Here is a 12 core processor, and I'm running it on a 32 GB RAM machine, and this is running on a GPU. Okay, and the computation is going to be faster. Okay, and in order to run these kind of simulations, very advanced simulations or mathematical computations, we are supposed to be using very high-end systems. Okay, 16 GB to 32 GB. 32 GB RAM will be wonderful with a NVIDIA GeForce GTX kind of graphics cards. Okay, and a minimum of 12 core should be advisable. Okay, and only then we will be able to run these kind of computations. Okay, so after running the computation, I have arrived at my result, and so this is what is the flow that is going to look like. Okay, so I have my this one, because it's a transient system. Okay, the transient system, I will have to make use of the time, because it's a time dependent function. Okay, the function is going to be with respect to time, so it can be the velocity with respect to time. Okay, and it is also how the viscosity and the other parameters, because for turbulent energy or for turbulence, we need to define the viscosity. Turbulence is a parameter that is going to be defined on viscosity. So the viscosity of water, the viscosity of air. Okay, and what is the kind of turbulent energy generated. Okay, so that will be at time t is equal to 0, how much it is, time t is equal to 0.1 seconds, 0.2 seconds. So like that, there is going to be about some 1,500, 2,000 iterations, so maybe 3,000 iterations. Okay, and it might take about 6 hours or 7 hours for such a computation. Okay, and very normal system with a 8 GB RAM or something like that, this will be taking you about say 8 hours to 9 hours, and a 16 GB RAM machine with 12 core will run the simulation in 3 to 4 hours. A 32 GB RAM machine, okay, with 24 core or 32 cores will be making it very faster. Okay, so because that's an exponential kind of trigger that you get in the computation. So here, let me play it, how the flow is going to happen. Okay, so this is how the flow patterns look like. Okay, so these are the bluff bodies. There are 4 different circles that you see. Okay, and whatever the shock loads or the waves which is generated at the nose cone of the submarine, okay, that is going to travel back, and it is going to so this looks exactly like the magnetic field. So the waves are like that. Okay, so now you see that behind the waves are going to be generated, and that is going to create a vortex. So these red regions, whatever you see, are the vortexes. Now, if we refine the mesh, the cells, whatever I showed you, the basic mesh or the advanced channel refined mesh. When we refine the mesh, we will find that these vortexes are well formed actually. Okay, so here we already have the vortex, okay, between the circular bodies or the bluff bodies. Okay, and now from this we can understand that there is a huge region, circular region, okay, with bigger waves, and there is a possibility for breaking these waves also. As you would have seen in front of the aircrafts, there is a sharp, a rod-like thing that comes. Okay, that is going to penetrate the waves and it is going to streamline it. So it is like the spherical bubbles of sharp loads or the spherical bubbles of the waves, the dynamic waves are going to be penetrated, that's going to be punctured. Okay, because very high speeds, very high velocities, the system is going to travel beyond the velocity of sound. Okay, that is called as the shock barrier. Beyond shock barrier, say Mach 1, 1.5, 2. Okay, what happens is the zone of shock barrier has to be broken, or otherwise that is going to create shock loads onto the structure and the structure can break, can blast. Okay, so now similar to that, even in the water, okay, there is a possibility for turbulence, okay, and these turbulences can be broken with such mechanisms. Okay, so now we have seen the velocity plot, and let's see what is going to be. So here it is almost about 64 knots, and then we have the orange yellow region, which is about close to 40, in between 40 to 52 knots. Okay, that's the speed, and then we also find the vortexes that is generated here. Okay, and then the system jets off, it goes off to the back. The waves are going to propagate to the back. Okay, now let's see what is the pressure. So now, yeah, this is going to be the pressure. So the pressure values are going to be in the range of 0 to 3.47 atmospheres. Okay, so let's see, like there are going to be very, very small regions where you will find the 3 atmospheres and all those. But then mostly you will find that it is between 1 and 2 atmospheres. Okay, so these are the zones where you will find 1 or 2 atmospheres. Okay, so this is how it's going to be pressurized, the submarines. Okay, so now what is the reason that we are looking for these kind of results? It's very simple, because the hull of the submarine, okay, it is again going to be like a thin shells. It's not a thick shell, it's a thin shell system. Now these thin shell can cripple. Okay, crippling is like because of a vacuum, okay, something can suck everything inside. And now what happens is, instead of outward bulging or an explosion, there will be an internal suck. So the entire system is going to get inside, and then the system can cripple. Okay, that way, either ways it can fail. Shell can fail into this. Outward explosion is one way, and inward deformation, there is going to be a crack or a fracture that can happen. Okay, so here we have seen the pressure. Now let us see what is going to be the mass fraction of air. Okay, so it's again, it is going to be varying between 0 and like 1. Okay, so now as I told you, we need to find out the mass fraction of air and mass fraction of water, not across the surface. It's not across the ocean bed. We cannot find that. because across the ocean bed we are going to that plane, we are just worrying, I mean, we will be only having what? Will be having only water. Okay, then there is no point in taking that. So instead, we can consider this particular plane. Okay, so that is going to be across the height of the submarine. Now, across the height of the submarine, we'll be able to find out what is going to be the mass fraction. So this is going to be the mass fraction. Okay, so the mass fraction of air is going to be 1 because air is on the upper zone, and blue color is going to be the water. Okay, so this is how the wave dynamics is. Okay, so yeah. So we'll be able to see how the air is going to cut open, or how it is going to move. It's going to slide over the submarine and then it is going to push forward backward. Okay, so here you will find the air is penetrating and it's moving backward. Okay, so here the air is streamlined. Okay, so instead of air coming forward and striking the submarine, let us assume that the submarine is moving at 60 knots. Okay, and that is going to strike the air, and when this air is going to strike over the submarine, it is going to carry the air towards the top, and then it is going to create a bend to the, so it will be something like an aerofoil. Okay, so it's like a aerofoil. We'll be able to find out the mass of air, mass fraction of air. Now let's see what is the mass fraction of water. So it's going to be the reverse of it, because the zone above the submarine is going to be water, air, and the zone below the submarine is going to be water. Okay, so now here the mass fraction of water is this. So we'll be able to find out how. So this is how it is going to be behaving. Okay, there is like it's all a matter of visualizing the velocity, the air. Okay, just try to see, like when you drive a car, when you are penetrating forward. Okay, there is a thick blanket of air or a tuft of air that is coming towards your windshield, and then it is going to cover the car, and then a part of it is going to strike the windshield, and it's going to sweep the hood and then go back, and a part of it is going to get circulated across the mirror, the side mirrors, and then those regions where the air gets circulated, those regions are called as vortex. I mean, there we will have a good amount of vortex which is generated, and now in order to break those vortexes is why the side mirrors are also designed in an aerodynamic fashion. Okay, the only thing is, like, you just bend it, so automatically the air will try to cut off and it will go back. Okay, now what we do is let's try to find out what is the temperature, because there will be definitely a change in temperature, because there is a work done. The work done is like it's nothing but the submarine is moving forward, and then there is a work done. Now because of that, there is going to be a change in temperature. Okay, and that change in temperature is nothing but it's between 19 and 20 degrees. Okay, so and moreover, we will have to get into the advanced. The more advanced, the more complex we get into, the more parameters that is going to increase. Now, if we try to consider that there are going to be about 10 or 15 heat bodies, heat sources within the submarines, now we'll have to account for all those thermodynamic parameters. Wherever the heat sources are there, so engine is going to liberate this much amount of heat, and then there is going to be some other systems. Maybe there are going to be some cafeteria or something inside, and there is going to be some cooking ranges. There are going to be some temperatures that is generated from that, and there will be some heat which is generated from the cockpit. So within the submarine, there will be a lot of electronic control units and weapons and warhead units, etc. Okay, that will be constantly under monitoring. Okay, and then these electronic devices under constant operation, that will also generate heat. And these heat, the small integral points of all these heats are going to add up the thermodynamic parameters. Okay, so then we need to define the heat flux of the system. We need to find out what are the convection factors, what will be the convection here. Is it air alone, or is it going to be only water that is going to surround the submarine? Okay, so that will involve a lot of thermodynamical parameters also. Okay, so now this particular system, we are going to assume that the system is a normal system. There is no thermodynamic parameters other than the nominal heat which is generated when the submarine is penetrating the water and moving. So that small amount of heat generation, which is almost about 1 or 2 degree rise, delta T is going to be 1 or 2 degrees. Okay, now let's see what is the volume fraction of the air. So this is the volume fraction of air. Okay, now there is no much difference. Okay, so we have the mass, we have the density. So density is equal to mass by volume. Okay, so now whatever mass fraction of air and mass fraction of water we saw, this is also going to be exactly the same, proportional to that, the volume fraction of air and water. Now let's see what is the axial velocity. So this is how the axial velocity is going to be. Okay, so let's try to find out. Yeah, so this is exactly yeah, this is a bit, the plane is a bit towards the outer side. What we can do is let's try to identify the zone. Let's try to identify that particular zone. Okay, so this is outward, and now this is going to be a bit inward. Yeah, so this is exactly the place where it is cutting the, yeah, so this is what we want. So this is cutting the bluff bodies also, and this is exactly cutting the submarine into two halves. Now the axial velocity we can easily find out. So this is how the axial velocities are. Yeah, you will find that there is going to be a velocity generated here. It's going to build up, then from there it's going to dip. There is a depression here. Then finally it reaches the first bluff body, then the second bluff body, the third bluff body, and from the first to second and second to third and third to fourth, there are vortexes developed. You will find that there is a tuft of air which is getting backward. Okay, so this is the axial velocity. Now let's find out what are the circumferential velocities. So this is how the circumferential velocities are. Okay, so now this is going to be like this. Okay, so the submarine moves forward, it is pulling the entire air, it is pushing the air backward. Okay, this particular region becomes the zone of compression. Okay, and now all those air that comes here, a part of it strikes on the top and then it goes, a part of it swirls here within the two bluff bodies, and then that becomes a vortex and gets accumulated here. Okay, so this is the circumferential velocity. Okay, so that's the reason, like the hydrodynamic is a very complex, vast system, and it's very difficult to visualize until you have a proper simulation tool and until you know the problem definition properly. Modeling, hydrodynamic, ocean hydrodynamic modeling, or any computation fluid dynamic system is going to be very, very difficult. Okay, so now this is the circumferential velocity, and now let's see what is the radial velocity. Yeah, so this is going to be the radial velocity. Okay, so as we know, in the previous sessions we discussed that any load which is acting on a structure is going to get converted into compression and tension loads. And now this is called as a direct load. Okay, then you have a bending load, then you have a shearing load, etc. So similarly, whatever pressure force that comes on a structure, so why we call it as a pressure force is the force created by air or fluid or any fluid structure with any viscosity, infinite viscosity or even zero viscosity, any fluid, when exerting a particular force on a certain area, we treat it as pressure. Okay. So similarly, there is going to be an enormous amount of pressure which is going to act on the nose cone of the submarine. Okay, that is what we call as hydrodynamic pressures. Okay, and now this hydrodynamic pressure, uh, we call it as a hydrostatic test pressure in thin shells or thick shells for the oil and gas industries. When we design the pressure vessels or the heat exchangers, we call it as hydrostatic test pressure. The same thing under the ocean, we call it as hydrodynamic pressure. Okay, so that's the difference. Okay, now these hydrodynamic pressures are going to be very complex. Okay, when there are going to be different dynamics. Here, the dynamics are not caused because of the body movements alone. The dynamics are going to be complex and it's going to be created more because of the structure, the geometrical structure of the geometrical shape, the size, the shape of the object, of the body. Okay, that is the reason the ship or the submarines or any floating structures that we design are going to be based on hydrodynamic parameters, factors. Okay, so now these radial velocity, circumferential velocity, the axial velocity, all these things are going to be the hydrodynamic parameters. Now we are going to find out what is going to be the relative, pressure. Okay, so this is going to be the relative pressure. So this relative pressure can have negative pressures also. Okay, negative pressures are nothing but the zone of suction is called negative pressure. Okay, so now you will find -1, okay, beneath the submarine. Okay, and at some regions here. Okay, and most of the other areas you will find it's almost closer to 1. Okay, so that is relative pressure. Then we find out a very important part, because see, when the aircraft is going to fly at a certain height, it is going to cause a good amount of noise. Okay, so now acoustic levels, acoustic pressure levels are supposed to be one of the most important regulatories in flying systems, the aircrafts. So the Federal Aviation or even the DGCA or the CIMILAC or any, CIMILAC is military intelligence certification, and then DGCA is Directorate General for Civil Aviation, so that will be for the commercial aircraft. And FAA is for Federal Aviation, again for the commercial aircraft. So based on these systems, regulatories, there is a specific range, the noise range. Okay, it should not exceed this many decibels. Okay, so now decibel is going to be the unit of acoustics here. Okay, and that is going to be derived from the hydrodynamic pressures, the shear factors, the shear stress, and all those things. Okay, from all the other velocities of the pressures, we are going to derive what is going to be the acoustic power levels. So now here we are finding out what is the acoustic power levels. Okay, so we will find that these zones, okay, there are zones which is having about 75 decibels. Some regions showing 75 decibels, some showing 68 decibels, okay, etc. And all the other regions are all noiseless. Okay, so now let's see how the sound is going to propagate. So yeah, this is how the sound is going to propagate. It's going to be propagating as a blob. Okay, so you will find that there is a big blob which comes, strikes the submarine, and then it goes behind, and then it strikes the bluff bodies, and it diminishes off. Okay, yeah. So this is how the acoustic noise levels are propagating. Okay, so these kind of simulations will be able to do only using computational fluid dynamics. A transient system with a computational fluid domain is what we call as a fluid structure interaction. This is going to be a perfect fluid structure interaction problem. Okay, so even using finite elements and nonlinear systems, explicit system, we can do fluid structures. Okay, but here it is going to be more realistic. So which means performing an aerodynamics using a computational fluid dynamics system and performing aerodynamics using a structural system by identifying the normal modes, operating frequencies, transient dynamics, okay, flutter analysis, okay, all these things can be done, but still the accuracy is going to be more when we perform a computational fluid dynamics, an aerodynamic, external aerodynamic simulation. Okay, so we have found out all these outputs, and now based on these outputs, hydrodynamic parameters, the structural design or the optimization can be further continued. Okay, so I hope this is a very interesting thing. Okay, the only thing which I would like to suggest you is you need to understand what is a finite element method properly. Then you need to try to understand what is a boundary element method. Okay, and what are the advantages of using a finite element method, and what are the advantages of using a boundary element method? When do we use a boundary element method? When do we go for a computational fluid dynamics finite volume method? Okay, and what are all the advantages of using a coupled simulation? So a structure and a flow simulation can be coupled together. So for example, when we try to find out what is the noise dissipated by the engine of a car, okay, this is going to be that the engine is going to experience firing, and because of the firing the fuel is getting burnt, there is a compression, and because of the compression there is going to be a blast, and because of that explosion there is going to be a certain dynamics in the engine that is going to push the piston within the cylinders, and each piston when it moves up and down, there is going to be a specific mechanism, a movement created, and this movement is going to trigger the crankshaft, and then that's going to move the flywheel, and then it goes to the tires through the transmission unit. So this is the actual process. Now in the particular process, what are the activities happening? So there is going to be a dynamics, okay, and then that dynamics is going to induce a certain vibration. Okay, so within the engine there is going to be a vibration, and this vibration is going to become a noise when the vibration is going to spread the vibration. The vibration is going to get dampened, or it is going to get transferred through the air actually. Okay, so this particular engine when vibrates, there is a specific noise which is generated, and this noise is getting diffusion to the cabin where the passengers and the driver is sitting. Okay, so similarly the noise is a big problem. That is, acoustics is a big problem. Okay, so that is the reason we categorize acoustics into fluid dynamics, because that is going to be analyzed in acoustics system. The acoustic formulation can be generated from the inverse of the computational flow systems. So which means from the flow, whatever formulations you get, the equations, the flow equations we have, okay, and to every flow equation, the inverse of that matrix is what we call as the acoustic domain. Okay, so it's a transpose. So let us say that there is a matrix A, okay, and the inverse matrix of that A, and then there is a transpose of that particular matrix. So this transpose matrix is going to be the acoustic tensors. Okay, so there is going to be a good amount of theoretical study also which is involved in this. Okay, but nevertheless, I would advise the engineers to also parallelly take it up from the practical point of view. Try to go through the theory, try to go through the practical session, visualize the theory and the practical session, okay, and then try to create a virtual session, okay, using the CAD and the CAE tools, and try to simulate it. Try to first understand the boundary conditions, which is very, very important. Okay, you must be knowing what exactly is the problem definition, and you should be knowing what would be the probable inputs that need to be given. Okay, and based on these inputs, only based on those inputs, you will be able to get the outputs. And you should also try to know what would be the boundary conditions. Okay, where how it can be, simulated. What exactly is a wall? How can we define a continuous wall? And what are the parameters, the boundary parameters that we need to define, and how we can generate the flow equations, how the flow files can be generated, and from the flow files, how we can create the acoustic files. I mean the noise, the acoustic power limits. Okay, so let me conclude this particular session here, and the next session that I would like to discuss would be more interesting. That will be on a blast. Okay, and why I wanted to show this before the blast simulation is you need to get a feel of fluids, and you also need to get a understanding on structures. And now overlapping the structure with the flow is going to be an explicit system. Okay, so that there we can model explosions more realistically. Okay, because these are all transient systems. Okay, there will be time dependent functions, there will be thermodynamic functions, there will be flow functions, and there will be dynamics also, all put together. It's a multidisciplinary system that is going to be discussed. Okay, so let me once again suggest you please subscribe this particular channel, share it with as many people as possible. Okay, try to make it more interactive, and you can make it more interactive by raising questions or queries or comments, and that is always welcome. We can definitely debate or discuss on certain topics, which is very much possible and very much invited. And we can also host some discussions on a certain topic, which is also welcomed. Okay, and let me again tell you, like, it's not only from books, or it is not only from any theoretical sessions that we can try to understand the problem definition and work. It is only out of sheer practice and real-time experiences that one will be able to gain it. And now I am trying to share my knowledge, okay, which I gained over the last 27 years within the industry. And as I told you, like, I started off my career as a CAE person in the industry, okay, and have been working extensively with many tools like Nastra, ANSYS, Abacus, many tools. Okay, and I have also worked parallelly with the industries, the manufacturing systems, the production units, and try to visualize the virtual, try to correlate the virtual systems and the real systems, and try to understand the boundary, the limits of boundaries, and based on assessments and based on experience, and putting a lot of effort on trying to learn the tools, because tool is a very important part. Okay, it's not only the technology or the engineering part or the domain part. Okay, the tools are very, very important. Technology and engineering can come out of domain. A domain can be, a domain is very important, and that will be taught from any institutions, universities. Okay, but then experience, the correlation part comes only out of sheer experience. Okay, so please subscribe, share the video, and you can also go through the other videos. So we have about 50 to 60 videos, and all videos are very meaningful, and you will probably be able to understand more from those videos. And please raise your comments and queries, and feel free to contact me through mail or through your messages. I'll be very happy to support you the best way possible. Okay, thank you. Thank you very much.